Hi everyone, welcome to Kotlin Conf, welcome to Copenhagen, and welcome to Kotlin's Elegant Deceptions, Simple APIs, Unusual Tactics. I've got a request, if everyone could not set fire to anything for the next 45 minutes, that would really help me out. So this is a talk about API design. Specifically, I suppose it's a talk about library API design, open source libraries. Well, I suppose at the end of the day, whenever we write code, we're always writing APIs for me or your team or some random people on the internet who might want to download it. And specifically, this talk kind of is about the kind of ways that we can use Kotlin and the Kotlin language features in kind of unexpected ways in order to actually be able to deliver simple APIs to our users. So first, a little bit about me. My name is David. Hi. I'm a technology consultant from London. I've been doing typing things about 20-something years. I've been using Kotlin since 2015, and I've used it in a few different industries like scientific publishing, banking, COVID-19 app, some general stuff. So it's nice that it's actually the support is there throughout the different industries. You can see me on GitHub. Most of you, if you know me at all, you'll know me because of my open source work. I'm kind of co-steward on the HTTP ecosystem. We've got about 150 odd libraries now in Maven. And I'm also a member of the Google Developer Experts program, which allows me to talk to you about Kotlin, which I love. So anyway, enough about me. About this talk. So why did this talk came about? So the talk came because people, I suppose, during our course of our open source work, we get questions about why we design things a particular way and how we've managed to actually kind of design for kind of maintainability. Because when we've done 1,000 releases of various sort of libraries, as we have, as I did a count the other day, it's important to kind of have things that are maintainable because any decision you make has knock-on effects. So what we're going to do, so we're going to talk about, that's why this talk, and we're going to talk about why Kotlin potentially is good for, and how it's deceiving you, and how it's kind of a good language to kind of lie to your users, as it were. We'll talk about a little bit about the kind of mantra for API design that we've kind of come up with collectively over 7 or 8 years of just how, what things do you need to take into account. And the majority of the talk is going to be about these, how we kind of apply these Kotlin language features. We'll talk a bit about the kind of problem we want to solve, and then how Kotlin can help us to solve this problem in an unexpected way, and we'll take a look at some code in the open source world. Initially, a word on words. So deception. Deception, unfortunately, has got a negative connotation, which is unfortunate because Cambridge kind of defines it as the act of hiding the truth, especially to get an advantage, which doesn't necessarily have a negative connotation because who doesn't want to get an advantage? And if we can do so without harming our users, then all the better. And besides, Kotlin is already lying to you. It's already deceiving you in all these ways, right? So these ways on the Kotlin, these language features that you can see on the screen, they're all lies. Whenever you see it, it's actually deceptive. So all we're doing is kind of finding out other ways that we can actually make our users' lives easier whilst kind of maybe deceiving a little bit. And good API design is just deceiving with style, is how I like to say it. So the mantra for API design, we kind of came up with a list of things that make a simple API, and we came up with these 8 things. I'm not going to go through them each one by one, but they can broadly be kind of divided into 2 topics. One, how easy is it for your users to understand the API that you've given to them? And the second one is how easy is it for them to operate the API? And when I say operate, I mean if they need to use it or extend it or test it, how exactly, what help do we give them to make it simple to operate? Fundamentally, an API's idea is the purpose of it is to hide complexity. And so that's really the thing. I think in our open source work, we really tried to kind of push that to the kind of boundaries. So the simplest API of all is a function. So a function is very simple because it should do just one thing by definition. And in a purely functional sense, the type signature of a function should tell you what it does. We've got list 3 function types commonly used on the screen, but let's take predicate, for example. We know it's basically a data transformation. We're saying, given this thing of type R, I'm performing a test on it, and I'm getting a Boolean back. It's a data transformation from a type to a Boolean. And that's all most functions should be if we're in a mutable world. And the thing is, if you can we use these kind of functions all the time. We use lambdas all the time. Every day, it's built into scope functions. It's built into the collections library. And functions are an API by themselves. We don't think of it because it's so ingrained into how we actually code and how we think that we don't think about it. And if you can extend that so that your users kind of forget that they're actually using an API, because it's so ingrained, then half your work is done already. They won't need to look in the documentation because they should be able to see it from the domain types that they kind of can see in their IDE. How we use that, that's kind of taken to an ultimate kind of extent in HV4K. HV4K, this is the core of HV4K. It's basically four effectively lines of code. There's one file in the middle of HV4K in the core that's just got these lines in it. The entire library is effectively two functions. One is a type alias with request response. We've boiled down what HTTP is into just a function definition. That's it. And the other one is the filter, which is just a decorating function. So you can, and given these building blocks, what you can do is take these then methods and you can compose the simple building blocks together to build bigger forms and more complicated things from these primitives. And this kind of approach we kind of try and use throughout the our open source work. And we use it we'll see a couple of examples on today, but this is the kind of core of, if you can boil things down to such a simple thing that your users cannot literally get it wrong, and they just have to learn these really simple concepts, then let them make their own world, give them the building blocks, and let them go wild to create their own stuff. What we can do once we've got these functions is compose them together to make more complicated wholes. So you can see on the screen what we've got is effectively we're building a kind of quite type-rich HTTP client. It's got some request tracing in, it's got some gzip, it's got some resilient stuff, it's got some routing and some security. But this piece of code only exposes the two types. It exposes HTTP handler and filter, and the request and response domain types, if you will. So although it does look on this bit of code that we're creating, for example, let's take request tracing. That request tracing function is only actually exposing the abstraction. There's no request tracing filter. There's no gzip filter class. Users can work purely in terms of the abstractions which they already understand. So let's just create an object. This is the most simple piece of code I could possibly kind of come up with. And it looks fairly simple on the face of it. But there are actually 6 ways of defining this piece of code. And I'm going to go through them now. The first one is, as you would expect, is a class constructor. No surprises there. The second one is a top-level function. The top-level function has a capital letter at the start, but this is OK as per the Kotlin style guide because the type that's returning matches the actual name of the function. The third one is we can use operator invokes, basically, so Kotlin gives you the ability to treat any object as a function if you define an invoke method on it and call it an operator. So we're doing this on an object here. We can then do a similar thing, but actually by kind of embedding the greeter kind of function inside another object. We can use a slightly different version of it by taking the companion object and putting the invoke function on the companion object, but that companion object belongs to an interface. So that's another version. And the 6th one is the good old extension function, which I'm sure everyone here knows how to use. So 6 pieces of code, and 5 of them are different, and 1 of them is a constructor. And the 5 that are different are factory functions. And each of these function types has its own place, it has its own use. And we use them again and again throughout the various 150 libraries that we've got. But there's a lot of power differential between these things, and let's compare how these things work. So if we're comparing constructors and factory functions, let's compare them. So return type. For constructors, the return type is constrained. You can only return the return type of the class that you're constructing. Perfect. With factory functions, you don't have that restriction. You don't need to return the same class. You don't need to. You can return an abstraction. You can return null. You can return an either or a result. You can go wild. Custom logic of constructors, you can't do it. I mean, you can do it with a run, but it's like really, it's not nice, and we shy away from it. The only kind of logic that you could do for, say, validation is doing an init block in the middle of your constructor that can throw an exception. With factory functions, you can go wild again. You can do exactly what you like. Bits of code, long, small, whatever it is, you can actually do it with a factory function. Advanced features like inline functions or reified generics, not possible in a constructor. If you pass a generic into a constructor, that type is kind of hardwired onto the type that you return. You can't pass a generic and vary that generic. Not so with a factory function. Once again, you can use those features exactly how we would use them in any other thing. The only difference is you're creating an object. Extensibility. Constructors are inherently invasive. If you want to add another constructor, you have to have access to the original code and the class, and then you can actually insert the lines of code where you need to. But with factory functions, once again, it's flexible. We saw 5 different versions of factory functions, and some of them are inside classes, some of them are outside classes, but you've got like options. And then last thing is, when do we want to use it? This piece should be more kind of renamed, when is David going to use it? David uses constructors when I want to actually expose the actual concrete type to the user, maybe because there's a bit of state on it they need to track. Factory functions, and what would I use factory functions? Well, we've kind of covered a little bit already. When I want to return an abstraction, when I want to vary my model, so I'm returning a null or an either, when I want to do some validation. All those, so given this kind of differential, the question for me that I kind of came across, when would I ever use a constructor? And the answer for me is only when I absolutely have to. For everything else, we tend to default to factory functions. So if we're looking in the open source world, we've got like discovery. So discovery of APIs are important. If we're not creating classes, then we need to give our users some way to kind of actually discover. And what we've got here is we're using this object kind of function, the object outer object as a kind of discovery point. So the user comes in, they type server filters dot control space, and they've got all the options that they can actually see. And anyone can then obviously attach other things. So you come up with another server filter in another project, you can actually just attach it because it's an extension function, and that's what Kotlin gives us. The bearer auth object in the center object is got 2 invoke methods which are overloaded. And we're using this bearer auth in order to kind of, this object to kind of group those 2 things together. It's kind of a logical unit that can be moved around. But the most important thing about this object is if you look at those 2 invoke methods, they're both returning filter. There is no bearer auth class, there is only a filter. There's the abstraction, and then there's the implementation of the abstraction. And that's kind of the key thing to, your users should know that there is an abstraction called filter, and there is this thing that's configured to do a particular thing. But they shouldn't have to worry about this class being having a different kind of runtime semantics or whatever that requires its own class or state. It's just there as it is. So body types. So we find another usage of the in HTTP we use HTTP bodies, and some of these bodies are the data is in memory and some of it isn't in memory. Some of it's a stream and some of it's in memory. But in order to kind of hide that from our users, we've got an invoke method on the companion object that returns one thing or another, depending on what they passed in. But we're also using the companion object here in order for our Java users to be able to actually use the static function nicely. So if you look at the last line of code, that's how you would call it from Java. So these are different mechanisms that have different places, kind of different uses throughout. And it's worth kind of thinking, doing this, using factory functions also gives you options to switch between the 2. Whereas actually if you had constructed a type that everyone was then relying on, and if you change that type, then you're going to break their code. So it's easier to actually rely on the abstraction. On the concept of discovering, or on the extending discovering, there's another type in HTTP called a lens, and Simon covered optics of it earlier. But a lens basically is 2 functions, one in one. One of those functions allows you to, taking a target object, extract a part from it. And there's another function which is basically to inject a part into it. So these 2 types of function, once again, they are just data transformations. We see a target and a part in extract. We're turning one thing into the other. So on discovery, because we've kind of defined this concept, we want people to be able to use it and discover it. So we have this thing on the left called the kind of recipe, basically. And the recipe defines how our users can actually find the particular lens and extend what they want and they can extend it for their own purposes. So first of all, we have like a target, and the target is the piece of, in this case, HTTP message, and it's like a body or a query parameter or a header. These are just static Kotlin objects. Then we have a mapping. The mapping says, once I've removed this query string from my request, I actually want to turn it into something else. I want to turn it into an int or a local date or a Boolean. And that mapping, these mapping functions allow you to do that. Now, these mapping functions are actually defined on the generic superclass that all of the targets extend. And that allows that's kind of, you can, we'll see that you can actually define these things once and get them reused throughout your code base. And the last piece of information we need is the cardinality. So that allows us to say, well, how many of this thing are we expecting? Are we expecting 0 or 1? That's optional. Are we expecting exactly 1? That's required. Or even a list. So given this kind of recipe, that allows our users to be able to find what they need and to extend it in a kind of simple way. This is how you would use it. We've got a query and a header. They're both called admin. One's optional, one's not. And they're both Booleans. So this is how we would use it. We'll define a request. We say, once we've built our lens with the recipe, you can see the lens of query and header. You can apply them to the request, and you either get the complete exact type thing back. And if the required header isn't there, then you get an exception. So how do we extend this ourselves? So let's say we want to create a file. We've got a query string parameter that comes in, and it represents a file on disk. And what we can do is we can write an extension function on the generic type. So the first 2 lines of code here are defining a type aliases, which is a biddy lens spec. That's the superclass of all the targets that we were talking about. And then we define the extension function on that generic. And that means that everything that extends that generic gets that function by default. And so you can see there's 2 implementations here. There's one an environment key and one a form field. We defined that file function only once, and it automatically gets inherited by every single inheritor. So another thing about building APIs is that it's tended that to be thought that using primitives is like bad, right? Primitives are raw pieces of data that have no domain meaning at all. But pieces of data in our domain do have a meaning. So using primitives allows us, it doesn't really allow us to kind of do at-front validation. It allows us for invalid data to enter our system. What we really want to do is make invalid types unrepresentable. Now we could use a type alias to make it look like, this string is called birthday, but there's no validation on that. So there are other concerns that we need to worry about, which is like validation and parsing, and even PII. If you want a bit of information that should not be shown or should not be accidentally outputted into a Datadog or Splunk because it's going to be a nightmare to get rid of and GDPR is going to kick in, it becomes really, really important. There's an implementation of of how we could use a value class to achieve those things. But that also has the same limitations we saw earlier. So we're relying on exceptions in order to actually validate our types. And there's lots of repetition. It's quite bulky. So what we want to do is kind of try and find a way to kind of reduce the boilerplate and actually make it as simple as possible in a reusable way. So, for that, we can turn to quite an unexpected source. We can turn to companion objects. Now, a companion object is an optional kind of object that you can include in any Kotlin object. Traditionally, it's where all the static state goes that would have been on a Java class. So that's how it kind of tends to be used. But this is really unfortunate because the companion object actually is much more powerful than that. It's a fully fledged object, which means you can extend it. You can extend other objects, other classes. You can implement interfaces. And once again, you can define these classes can be have inherited functions that can be used by every single type. And the last thing with companion objects is you can actually you can pass them around as singletons. So when you import a class, the companion object is inherited for free implicitly. So that's kind of you've got 2 objects for the price of 1. So how do we use it in the open source? So we've got values for k. Values for k is a tiny type library from fork handles, which is another kind of platform of modules that I'm involved with. And what we've done here is to try to compact all of the shared functionality like parsing and validation and display logic into a set of kind of reusable classes that can then form the basis of the companion objects. And they're called value factories. So you can see the party date on the screen. It's got its companion object extends local date value factory, and it's got an epoch min value as a validation. And the validation basically says you can only construct a party if it was after 1970, January 1st. So if we see how we can use this, the party date.of function that you can see in the first two, those functions are defined on the generic value factory superclass. So we have an of method, we have an of or null, we have an of result. If you want to add an of or arrow either, terrible name, but then you just need to define it once, and it will be inherited once again by every single class, every single microtype in your entire stack. So the other thing we talked about PII and how to accidentally, if you accidentally display these things, what will happen? So if you try and print out that party date, because the party date is PII, it's a secret, you'll get a masked value. And the reason that masking happens is because of the top right, you can see the hidden masker that gets passed into the constructor. If you actually want to reveal the date, we can use partyDay.show. And that show method is once again on the generic value factory object, and it's inherited by everything. So we've got a bunch of rules to do with masking, kind of show and to do with validation and parsing, and they're all kind of packed into this small space that can be reused again and again. And then how do we use that? So I said we can pass around the companion object as a singleton, and we can see that here. We've got a value function, which is an extension function. As we said before, we did with the file object, that's an extension function on the generic super type, and we pass in the party date, and that gives us a typed lens that will automatically take into account the parsing rules and the display rules logic to give us a one-liner lens that will actually allow us to remove typed data from the request. So it's really, really useful. Extension semantics. So extension functions are great. Let's say what we want to do here is we want to create an encode a number to a string, and we want to use base 2. We can define an extension function for encode and decode, and then we can use that extension function. Brilliant. But the semantics of extension functions are kind of broken as to what we would expect if we have a generic piece of functionality that we want to implement again and again. If we want to implement base 4 encoding, we can do the same thing again. We can define an encode and decode method with a 4 instead of a 2. But we have to put it in a different package. So those two things, if I want to then go and define a base 8, there's no way of me telling everyone that, oh, if you want to do your own encoding layer, what you actually need to do is implement this kind of encode and decode, right? Because normally we'd use an interface to this. And the thing that kind of I was really interested to notice was that you can actually do this. You can define an interface with an extension function being a part of that contract. So this is the base 2 and base 4 implementations reimagined as a part of how we would use if we had an object. So we're defining a singleton for base 2 and one for 4. And they don't cross over. There's no pollution between the two because, if we accidentally import the wrong thing, it's, we're not going to get that problem. So if we want to actually, this allows us to use, there are two ways to kind of use it. And the first one is to kind of maybe have let's say you're in a global encoding system, you decide you're going to have base 4 or base 2. You can define a type alias, which defines your chosen encoding system, and then you can use it as import everywhere else. And if you want to change your entire system to use base 2, you just change that one import into one place. So that's like a convenient way of getting a really far-reaching effect without everyone having to go and update 900 different files because they're all using an import from somewhere else. And the second way to kind of, if we want to do a slightly more type-safe way, we can use the with base 4. That brings the base 4 into scope, and then inside that base 4 block, in that with block, we can actually use those extension functions, and it will automatically inherit from the the wrapper, the with scoped. We use this in HTTP. We use it as message formats. So we support a bunch of message formats. We support Jackson and JSON and Moshi and XML and stuff. And it's not particularly interesting, but it's basically like they all have this same contract thing. So we want to implement a new encoding system or for a new format. We know we've got our contracts. We know exactly what we need to do. A set of tests that need to be actually a common set of tests that need to be implemented across everything. And so that's the real power of that, is that you're kind of forcing that contract. It's just as you would with any other interface, but you're doing it and also getting the benefit of an extension function. So, bridging static and dynamic data. I like to think of data classes as like the ultimate in static typing. We're using a statically typed language. So not only do you have to define your vals on your vals and your vars in the constructor, but also when constructing one of those objects with a data class, you have to give it all the values, right? So there's absolutely zero option for it being dynamic. But the problem is here is that, and we can update this value DB port, we can just set the value to something else using a var. But the problem is here that we don't do this. We don't have static objects. I certainly hope we don't have like usernames and passwords and URLs encoded into our code that then get shipped off somewhere. We get them from some kind of dynamic or secret store. So if we wanted to kind of go down that path, we need to go round the houses to kind of make things more complicated. We need to create create an abstraction called a DB config repo, and then you need to load that DB config directly from the DB config repo. So from the user's perspective, not only do they have to jump through these extra hoops, but it's not, that data will forever be kind of hard coded in that instance, because that's what data class is. And you can see here that you've got, if we're creating this Redis example, for example, where we're reading all the keys out of Redis, one called DB URL and one called DB port, and then we munge those types, one into a URI and one into an int, and if it blows up, then it throws an exception. There's duplication here between the DB URL that's in the constructor of DB config, and that's also the key that gets read out of a Redis cache, for example. And so it's a bit of a contrived example, but the idea is that once you've got that database config option, that class, it generally doesn't change. So if somebody changed it under the covers and you wanted to read out the latest version, you'd have to completely reconstruct your DB config. So Kotlin provides delegated properties to us. Now, Kotlin properties are already one of these things that are deceiving us, because when you define a val or a var in a class, unless you define it as a JVM field with annotation, the Kotlin compiler creates a get method and potentially a set method if it's a var, under the covers, and so the actual bytecoder's got that stuff in it, and that's what actually what you're calling in your code, and that's what Java users, if they're using your Kotlin object, would call. But Kotlin allows us to kind of provide this custom kind of computation at runtime behavior with delegated properties, and that allows us to kind of override the actual, override the loading and the get and set logic. There are a bunch of these built in. We use the by keyword to kind of signal to Kotlin that that's what we're doing. The ones that are built in are like lazy, as in this example here, where we're reading the same value twice, but it only gets computed once. There's also by map, there's by observable. I'm sure I'm missing a couple, but but what we can do is actually we can provide some custom behavior based upon this this kind of technique. We do that using custom delegates. This example on the screen is like a strings class that is basically every time you call the next val, it's every time we call the next val, it's computing a new value that then gets returned. So we create strings, then we call next, and we get two different values out. And we use the by keyword, and we implement read-only property on that property. So that property itself that's just an interface. I think it's an interface. It might be an interface. It might be an abstract class. I can't remember. But it's got this get value method, and the read-write property, if it's a var, has got a set method as well. That method takes the thisRef, which is the instance of the class that you're calling this function on, the next value on, and it also passes in the property. That property, you'll notice, has got the name that is available to it when we're calling it. That means that we don't have to say next hard-coded at this point, because it comes from the property name, and then it appends the counter that's been defined. So we use that a couple of ways in open source. There's data for K. Data for K is a data-oriented programming module from Fork Handles. And what it allows you to do is to interact with a dynamic data store, like a JSON node or a map, in a kind of infinitely deep way. And effectively, what it's really good for is putting a kind of static sheen over the top of this dynamic, this JSON node. So I can have a JSON document with 1,000 properties in it, and I only care about 2 properties. So what I can do is actually say, well, I'm going to define one of these things, which is like a data container. I'm going to pass in the actual document that I've just parsed, and I'm going to define 2 properties. And those are the properties that I care about. And you can actually also, what we're doing here is actually creating it, reading out the DB URL, which is reading out of the bit of JSON. But then we can also do the DB port where we're actually setting the value. And you notice that the required functions here have like a type coercion as well built in. So because we can reuse these functions again and again, we can define different types that have different type coercions, and we'll also as kind of like extension functions themselves, and we will get like that. We can build custom ones just for our own domain. So that's really useful. And then seamless Redis storage. So yeah, the last piece of code I'll show you is if we go back to our Redis example that we had earlier, HTTP Connect, which is the connector library that comes with HTTP, has a way of writing things to S3 or Redis or anything else by using what we call a storage bag. And what this does is, using a similar mechanism to what we just saw with the data for K, with the JSON, it will actually read and write values into S3 or Redis or whatever you want to write a storage abstraction for. It will do that seamlessly, and the user themselves don't need to know that you're necessarily, they don't need to think about talking to Amazon. Now, obviously, there are concerns to do with, what's the operational concern if Amazon's down, et cetera, et cetera. But it's just an example of how you can actually, the user API experience is a lot easier. They don't need to call directly all the way down into S3 or have an S3 client. You actually provided them with a piece of code that's actually, doing that for them. It's all still like just making your users' lives as easy as possible, and that kind of really pays dividends. So that's kind of all I really had to show you. In a nutshell, I think we've learned that you can decompose. If you can decompose your types, your problems into particular small parts, especially if you're building an API, and then to kind of ship those primitives to your users and let your users kind of build their own world themselves with the primitives that you provided. And the easiest way of doing that is with the simplest possible interface. And a lot of times, the simplest possible interface is just a function. Aggressively minimize API surface. This will give you the option to change your mind in the future, and it will give also your users less stuff to think about. Right? If they only have to think about these 2 abstractions and these 2 data classes, as opposed to having 10,000 different types of class they need to worry about, then that leads to that kind of decent, nice experience where they go, oh, I understand that. I can actually build this kind of model up myself. And the nice thing about composing more complicated parts out of the primitives is that it's such a powerful technique that once you'll be surprised at how how many times you can reuse it if you kind of can get to this this stage. Companion objects are real objects too, because try and use them for all of their functionalities. Beware extension nameplate solution, because extension functions are great, but they do come with a downside where you accidentally might import the wrong thing. And finally, investigate good APIs. If you see an API and it looks nice, just dig under the covers, because you never know what you might find. Anyway, and that's all I had to talk about. Are there any questions? Oh, before we actually have questions, I'd say that we're really stoked that Kotlin 2 came out this morning. It's brilliant. We've upgraded HTTP, and I stood here and released it 2 minutes before I actually started talking. I wasn't stupid enough to actually do it live. That'd be ridiculous. But it's taken a minute off our build, so thank you, JetBrains team. Anyway, right. Any questions? Thank you.